which the work I'm going to be talking about today is probing the effect of these two types of pressures on these two materials to try and then sort of gain a better understanding of how pressure affects pharmaceutically relevant materials, especially when they're being tableted. So first, let's look a bit of at pharmaceutical tablets and pressures. So I'm sure many of you this week, if not today, have taken potentially a tablet. So tablets are just key products in the pharmaceutical industries, and that is shown as they are the most widely used oral solid dosage form worldwide. So they have a convenient design that favors high patient compliance. They also display a good stability to atmospheric conditions, and they can be manufactured at a large scale with a correct formulation in a relatively straightforward way. So during this tablet manufacturing process, at different steps within the production line, a degree of pressure, which might be considered relatively low in more of like crystallography point of view, so up to 0.3 gigapascals. So this sort of pressure is applied to the pharmaceutically relevant materials. And so whilst this pressure is still relatively low, it can have an effect on the properties of this material and the final quality of the tablet, as it can affect its mechanical properties, the solid state properties, and also the chemical stability of the materials. So with mechanical properties, exacting a pressure will define a change within the elastic and plastic deformation as well as fragmentation, which ultimately then impacts the physical attributes of your tablet and its overall quality. With solid state properties, we have seen many examples where pressure has an impact and affects this polymorph change within your material. So if we see here, for example, mannitol, upon 6 hours of milling, we can go from the stable beta form to the metastable alpha form. Additionally, for glycolite, upon direct compression, so using hydrostatic pressure, we can see how the ambient form changes to this high pressure form, which can then remain up to around 2 weeks upon decompression. So these examples just show how it's really important to sort of have a good understanding of that pressure, because even if we make a tablet and we think it's one form at a time, it could be waiting for 2 weeks and then just change that form. Finally, there have been some cases also where this pressure has affected the chemical stability, and it's led to the formation of impurities, which is pretty much the last thing you want in your tablet. So whilst pressure is used, as I've said, at different stages, and it has a really direct and significant impact in the tablet, this relationship between the structural characteristics of your pharmaceutically relevant material and their behavior under pressure is still not very well understood. So currently, the pharmaceutical industry uses iterative testing to determine an oral solid dosage formulation that will have the adequate mechanical properties for tableting and also will retain the solid form that their scientists want. However, of course, we want to move away from this because iterative testing, it just requires additional funding, prolonged research times, and an additional amount of starting material. So traditionally, the pharmaceutical industry has studied pharmaceutically relevant materials more at a macroscopic level, so looking at those mechanical and tableting properties. What we want to do, especially in my PhD project, is feed into that and then start looking at these materials also at a more molecular level by using high pressure X-ray diffraction and Raman spectroscopy. And then we seek to just combine all of this information into an extensive experimental database. So that would also be complemented with all the entries seen within the CSD drug subset and the high pressure subset. And from this experimental database, we can start extracting information to try and understand the effect that pressure has, and then at a later stage in the future, hopefully begin using that understanding to then predict how a material might behave under pressure, especially small organic molecules, so those are pharmaceutically relevant. So in order to start feeding into this, I've been looking at two different molecules, which are ofloxacin and levofloxacin. Instead of picking some molecules that have been extensively studied, we decided to go for these ones, firstly because they are extremely relevant. They are broad spectrum antibiotics, which means that they can be prescribed for both gram-positive and gram-negative bacterial infections. Secondly, they have a really nice structural similarity, which means we can do a more direct comparison between them. So the only difference between the two of them is this methyl group down here. That's for ofloxacin. It's in a racemic nitrogen. For levofloxacin, it's just the levo isomer. Additionally, there is a degree of molecular flexibility within this molecule that would be interesting to study and how it might change under pressure. Also, it was quite surprising to find that these two molecules, while they are structurally very, very similar, they have quite different solid state landscapes. So floxacin is quite happy just recrystallizing in the anhydrate form in just one single form. However, levofloxacin, it can recrystallize in a variety of anhydrate or hemihydrate forms, as seen in this slide. To go further, we only have studied the ones highlighted either in blue or in this reddish pink tone because they're the most easily accessible forms to crystallize. But that doesn't mean that in the future I'd want to kind of get a good idea of all of the forms. And then finally, both, all ofloxacin hydrate, levofloxacin hydrate, the gamma form, and levofloxacin hemihydrate, they all have distinct slip lane systems. So what is a slip lane? Slip lanes can roughly be defined as just the planes in a crystal structure where there's the weakest interaction between the adjacent planes, and they account for having the highest molecular density and also the largest d-spacing as compared to other planes. So within a slip plane, you have the two planes, and there's a glide displacement of these two planes, which that would be different to, say, twinning, where there would be no displacement, but just a change in orientation. So for slip planes, there's no change in orientation within the different planes. So slip lanes are quite a nice thing to look at because they can be seen both at a molecular and then at a macroscopic scale when being studied under pressure. So it is well reported that the presence of these active slip lanes, that means that do glide, are responsible for a degree of plastic deformation in organic molecular solids, including pharmaceutical solids, which is what we're really after. So to sort of look at the potential slip planes in the systems that I've covered in this slide before, we've been using the CSD particle. So that's a tool but especially my supervisor here at the CCDC has been sort of working on over the last 2 years. And it's a tool which combines a set of topological crystal structure descriptions. So then all combined, they can be used to predict slip planes that might be plausible within your structure. And you can also look at the geometry these potentially will have and whether there's any hydrogen bonding across the slabs within the slip plane. Just also to bring it up, an example of a very good, well-known how slip planes might affect this plastic deformation is paracetamol. We can see the top form 1 is just these very flat planes with a slip along them, which is active because there's no hydrogen bonding across it. So that provides the form 2 with high tabletability and high plasticity, which is not then the case in form 1, as there are just there's no slip separation with a slab separation above 0 angstroms. So for the slip planes in ofloxacin and levofloxacin, we sort of studied all of the plausible ones that would go down to a slab separation of minus 2.0 angstroms. So I know the idea of like a negative slab separation might sound a bit confusing, but this just means that the slips are interdigitated. So it's as I was interlocking my fingers like this in a hand. So the left-hand side of the diagram, you can see, for example, a separated slip. So while there's rugosity to it, the planes are not interlinked with one another. So both planes can glide along it, whereas on the right-hand side, there's some interdigitation between the planes. There's a bit of interlocking. So if you were to move the planes along the same direction, it would go up and down. It would be a bit of a clunky movement. Therefore, to sort of study these materials, or at least sort of get an idea of how they might compress through the slip planes that they might have, we only really looked at the ones with a positive slab separation to sort of try to avoid any potential interdigitation. So these are the slip planes that we saw. So it's quite interesting how in space, both the ofloxacin and levofloxacin anhydrates formed, they sit in space in a very similar manner. However, they have quite distinct slip planes. Ofloxacin anhydrate, there's a high rugosity. I wouldn't expect it to glide a lot. However, this is not the case with levofloxacin anhydrate. There's a larger slab separation. It's quite flat, and I would expect it similarly to paracetamol form 2 to have a nicer glide along them. For levofloxacin hemihydrate, there were just no slip planes calculated with a slab separation above 0 angstroms. To look at these materials, we went to the European synchrotron radiation facility to carry out some high pressure powder X-ray diffraction. So both of the materials were studied inside a diamond anvil cell, and they were studied under different types of pressure. So we looked at hydrostatic pressure and also non-hydrostatic pressure. This is because ideally, when you would study a material, it would be under hydrostatic conditions, but of course, this is not the case when you make a tablet, as there's just the direct application of pressure in a non-hydrostatic way. So for the hydrostatic pressure, we decided to choose 2 different pressure transmitting medium, which is what you surround your sample in. Here in the gaseous chamber, just to apply the pressure to your material. And we went for petroleum ether, for which ofloxacin and levofloxacin are not soluble in, and then a 1,2,4-methanol ethanol solution, which shows a slight solubility for ofloxacin anhydrate and levofloxacin hemihydrate, the gamma form. So let's first take a look at the high pressure powder X-ray diffraction plots. So on the left-hand side, there's no pressure transmitting medium, so non-hydrostatic pressure. Right-hand side, 4:1 methanol and ethanol, so hydrostatic pressures. I haven't shown a plot for petroleum ether because the behavior was quite similar to that for methanol ethanol. So we see as pressure is applied, there's a sort of loss of crystallinity with our samples that seems to then be slowly regained as the pressure is taken off. So for no pressure transmitting medium, we didn't then take a final collection, again at ambient pressure, because we were having some difficulties with the detector. So yes, so for ofloxacin, so when using non-hydrostatic pressure, we don't really see a change in phase transition, but then the powder pattern is very broad. So unless it would be a very, very distinct phase transition, we wouldn't be able to see it. However, for hydrostatic pressure in a 4:1 methanol ethanol environment, we do see this potential phase transition happening at 7 GPa. So then we did a polyfitting of all of these powder patterns, and then just plotted all the different unit cell axes, the Beetle angle, and then the volume over pressure. So what we see is overall is quite a nice decrease in all of the unit cell axes. Is being compressed quite nicely. There does seem to be sort of a discontinuity for no pressure transmitting medium just before the 2 GPa mark, which we think would potentially indicate maybe a phase transition. Would we need to look into it further using crystal X-ray diffraction experiments? It's also quite interesting to see how with non-hydrostatic pressure, the compressibility is significantly less than for hydrostatic pressure. Yeah, that would just be, again, interesting to look a bit more further. When we roughly fitted all this data to the equations of state, regardless of whether it might be phase transition or not, we obtained quite small book modulo from like 8 to then 6 GPa, around 6 GPa for the non-hydrostatic pressure transmitting mediums. Plus, this is at the lower end of the molecular solids. We do sort of expect it, since there's only intramolecular hydrogen bonding in these structures, and they're not very very tight interactions between one another. So to complement this data, we want to obtain some single crystal X-ray diffraction data to see whether we observe the same things, and then get a bit more information with the atomic positioning space of the molecules, because for the powder patterns, they were just a bit too broad to do some real refinements on them. So this is the data that we have so far. We can see that there's a good agreement. Overall, it seems like around and above 2 GPa. The single crystal data sort of seems to be tailing off a bit. It seems to be a bit more compressible by the powder, but we just have to like keep going up to 7 GPa and then see what we get for it. So overall, the conclusions is that we saw some potential phase transitions. It's also interesting to see that for when using non-hydrostatic pressure, this potential phase transition is at a lower pressure, which could be because there's a greater stress experienced by the particles, as there's a lot of direct particle-particle interactions. So in order to verify whether these are happening, we are collecting now single crystal X-ray diffraction data for structural comparison, and to see whether we do also see these potential phase transitions. Now it's going to be a bit complicated for not using pressure transmitting medium with a single crystal, because it might just crack. So we'll be just using a pressure transmitting medium with a very low hydrostatic limit, such as silicon foil, to apply pressure. We also see this systematic different compressibility under non-hydrostatic and hydrostatic pressures. We are thinking it might be, again, because of this increase in the particle-particle interactions where there's no solvent surrounding the particles. So instead of them being compressed and then the unit cell parameters compressing, there's a high interaction, higher stress, so they fragment and they break, and they're just filling in the voids that there might be in the structure. So instead of being compressed, they're just breaking and filling voids. So then overall, you see this higher or less compressed unit cell axes. And then finally, it's just a matter now of also finalizing, analyzing all this powder X-ray diffraction data for the 2 levofloxacin samples, and then compare with ofloxacin and see whether you see compressibilities that might be related to the slip planes that we observed with the CSD particle tool. So finally, I would just like to acknowledge my 3 supervisors, so Ian, Daniel, and Andy, who's from the CCDC, as well as the staff from the ESRF Beamline and Martin Ward within the research group and the funding bodies for funding this PhD. Thank you very much.
That was super. Thank you very much. Just give you a round of applause there. Lots of people think. So I'll immediately put the call out. Are there any questions for Julia? Oh, we do have one. Simon, go ahead, unmute your mic and ask away.
Right. Hello, Julia. Nice talk. Julia, how reliable do you think a ruby fluorescence measurement is in the absence of hydrostatic medium? Okay, let's just think of a limit, right? If you had a completely empty cell and no hydrostatic medium, and you know, screwed the Allen keys together, you would probably see no change in pressure at all no effect on the ruby at all, because there's nothing compressing on it. If you have hydrostatic medium, of course, then that's uniformly distributed throughout the cell, and the pressure that you can imagine that the pressure that you actually get on the ruby is what's being applied to your sample. But it seems to me that if you have a powder with no hydrostatic medium present, you're between those two limits. And I wonder what you think about how reliable the pressure measurement is in the absence of hydrostatic medium, and could it be that you're just not applying as much pressure to the ruby as you think you are, and that you see that systematic deviation in slide you showed on, I think it was slide 8, where you between your points.
Sorry.
No, go on, Julie. I'm talking.
I was going to say, yes, it's not the most reliable. We tried to pack the cell with as much powder and sort of fit it between 2 powder layers, so it would experience a bit of like the pressure inside. Whilst there is a certain level of variation, it was pretty much consistent all throughout. And then I'm not sure whether at this moment we could use another material or another technique to just
could you mount several rubies? I mean, if you mounted more than one ruby, then you could see how much the pressure was varying between the different rubies.
Yes, I guess you would also then want to put rubies either closer to those diamond coolets and then between the powder, because there will be a difference in the pressure experienced, but that would again be a bit complicated to make sure that you're doing it evenly. That would be a good way, I think, better way going forward.
All right, thank you, Julia. That's great. Good talk.
Laszlo, do you want to unmute and ask your question?
Yeah, hello. It's very nice talk as well. I'm kind of reacting to Simon's question in a way that I think one other interesting thing is to see in this difference is how much does it depend on the microstructure of the powder. So say if you have powder fractions of different sizes, that could again, I think, give you some idea about how much variation there is, because that was one of the things that puzzled me in these results, is that I would expect the powder when I compress to comply a bit, so to feel, to adjust macroscopically. Did you see much evidence of that, or is it that low pressure settles somewhere and not much change from then on?
So to see a bit more of the fracturing and then the change of the size of the particles, I think for example, using terahertz spectroscopy or another technique might be a bit better to give us a good understanding of this. I'm hoping to complement this then in the future with the more compaction studies of making tablets and then analyzing them with terahertz. And then we can see when these voids are changing. We can also, for example, get a particle size distribution, see how that it has changed under pressure. So I think we would need sort of experiments like that to give a better understanding of this.
Yeah, thank you. I agree.
Okay, well, in the interest of time, keep us going. That was an excellent talk, Julia. Thank you very much for that.